here yesterday, the website is seeclab.com, seeclab.com. And if you go to teaching and 325, and the password is 325 summer, but I was logged in anyway, so the password is 325 summer. And everything is up there, so the syllabus is up there, the lab, lab and the lecture schedules are up there. I've placed the notes, and I'm working on slides as well, so I've placed notes and slides. So the notes were Dr. Bina's notes, and I'm working on slides, so I put the first set of slides for chapter 2. I didn't put slides for chapter 1. Yeah.
What's the model again?
325 summer.
Okay.
325 summer. And so I'm, updating this as we go. I put all the labs that we have, 2 options for mini project, or 2 variations for mini project. And then I record all the lectures. So yesterday's lectures are already up there. So you can, if you missed yesterday's lecture, you can watch that as well. So it's already up there. I will be, again, this lecture is recorded. Your first homework is up there. Our first exam will be next week, Tuesday. So next week, Tuesday will be the first exam. So I think you missed a lot yesterday. It's okay. So we'll get started. Huh? Yeah, I know. Actually, in chapter 1, we're going to do most of it, and then we're going to skip we're going to skip, a good amount of chapter 1 and do it with chapter 3 because it discusses the physics of semiconductors and introduces the diode. So what we're going to do is only the part that talks about, something related to 314, like signals and systems and amplifiers. That's the part that we're going to do. So it's half of chapter 1. So that's why it's okay to do the exam. Okay, so yesterday we stopped at, we stopped somewhere here. We were talking about, the objective of the class mainly is to deal with, sensor signals, take the sensor signal, figure out how to send it to a signal processing system, right? Our block is the block in the middle. This block in the middle is where we are going to be interested in 325. So this is the 325 interest level. We have a sensor. This sensor is either going to be modeled as a voltage source with a resistor in series, the Thevenin equivalent circuit of any device, or there's an equivalent, Norton equivalent circuit of any device, right? So there will be a current source with a resistor in parallel, right? And then we will typically have, take this sensor and connect it to a system, right? This connection to a system is, we will represent, again, if you're connecting a sensor to a system, and this system is drawing a little bit of current, I can represent that, approximately as a resistor, like I did here, right? So I can represent that approximately as a resistor, okay, like we did last time. Yeah. And in this case, this is the sensor current, this is the sensor resistance, and this is the RP as I put it here. Does not really matter. So what we said last time was the following: if forget about this block in the middle, right? We just have a voltage source with 2 series resistors, right? This voltage source and this resistor are representing my Thevenin equivalent circuit for my sensor, and this resistor is sort of representing my measurement system, right? If that is the case, what is my objective? My objective is to measure the sensor voltage. The sensor voltage is what's corresponding to the physical phenomena that I'm measuring. So I'm measuring temperature, light intensity, whatever it is. This sensor produces a voltage. This voltage is what I would like to measure. Ideally, I would like my signal processing system, which is represented as RP here, to see Vs. I would like to measure that. I don't want to disrupt that, right? So if I would like it to see Vs, basically I would like ideally V input to equal Vs. That's my ideal situation. For V input to be equal Vs as much as possible. Of course, it's not possible 100%. This is an ideal world, right? So what does the real world give us? The real world tells us that V input will really be equal to Vs multiplied by Rp over the sum of the 2 resistors, right? And we said yesterday that since this is the case, for me to have V input as close as possible to Vs, I need what? I need Rs to be a lot smaller than Rp, right? If that is the case, if RS is a lot smaller than RP, I can neglect RS in this summation, and this fraction is 1. I can approximate this fraction as 1, right? Or, in other words, ideally, I would like RS to be 0, right? If RS is very, very small, right? Ideally, it's 0. If RS is 0, then this RP over RP is 1, and V input is equal to Vs, right? So, and then there's a corresponding logic in if a sensor is represented as a current producing device. We said yesterday some sensors can be represented as voltage producing devices such as maybe a micro generator that is connected to a mechanism that measures flow. This micro generator is producing a voltage, right? This is represented as a Thevenin equivalent circuit this way. I can have another sensor that is a capacitive based sensor, right? So maybe the capacitance is changing. If the capacitance is changing, capacitance changes, or the value of capacitance will correspond to will limit the amount of charge on the capacitor, for example, right? If you have a certain voltage limit for that capacitor, a corresponding charge will be allowed to be deposited on the plate of the capacitor. Changes in charge will correspond to changes in current, right? So I can represent that sensor as a current sensor, for example, and I can move from Thevenin equivalent to Norton equivalent easily, right? We know that from 214. But in this case, what would I like to measure? I would like to measure this sensor current. I would like that my signal processing system sees sensor current. I can call this VI input, for example. I would like ideally what? Ideally, I would like I input, in this case, to equal IS. Same logic, right? If that's the case, what do I need RS to be? Okay, let's do current divider rule. I input is equal to what? IS
RP, RS plus RP.
RS over RS.
Is it the opposite way? Oh, yeah.
It's the opposite
Take
branch
the
over
opposite, yeah.
RS over RP plus RS, right? So what do we want here?
RP too close to 0. To be as close to 0.
RP would be
Much
close.
RS, I'm sorry.
Oh yeah, we need RP to be short circuit.
RP would be ideally you would like it to be small. That's one way to go. Or another way to go is what?
By looking at the ratio RP.
Because if RP is small, it's sure. But what is remember what's the restriction on RS in this case? Because here we came up with a restriction on RS. We would like it to go to 0. What would be the similar restriction on RS here?
It can't be close to 0 because it would create a short, wouldn't
Yeah, that's why it would be a short circuit, right? So it would be if it's a short circuit. If
Then
it's a short
RS
circuit,
has
it will
to-
still. If it's short circuit, if it's 0, then it's not going to work.
RS should go to
No. If it's exactly. So if it's 0, then I input is equal to 0. Right. So that's not going to work. So what's the limit? What's the
RS has to go to infinity.
exactly? Right. So if RS is very large, or RS is much larger than RP, here it was much smaller than RP. So if RS is much larger than RP, then I'm happy. Right? Like this fraction is equal to 1, almost equal to 1, and I input is almost equal to IS. Okay, so that's the analogy. Yes.
Why don't we look at RP in this case? Why don't we say RP goes to 0?
RP goes to 0.
So it becomes a short circuit.
Because then it would be RS over RS.
Like this is our load.
But then we can't control the load, basically. That's why we...
No, what do you mean you cannot control the load?
RP is the load, right?
RP is your signal conditioning system. Yes.
Yeah. So why can't we make it go to 0?
We will find that if you have something that is if you have an input impedance to any circuit that is 0, what does that mean? That if I put a voltage source at that input, this is modeled as a short circuit. If it's a short circuit, then current will be flowing here. Ideally, I do not want to have the sensor send power to my signal conditioning system. I want to only sense the signal. Right? So I would like to only sense the signal. I do not want to be consuming power from that. The whole issue is these sensors are not able to produce power. they can produce a current that is proportional to a physical phenomenon, a voltage that is proportional to a physical phenomenon. We don't want them, they cannot produce power. So, and that's where we will be putting somewhere in the middle, something in the middle here. If we put something in the middle here, then what can I do? If current is flowing into this circuit, remember this is a voltage source, this is a voltage source with the sensor resistance and then my load resistance, right? I was able to come up with a recommendation for RS and RP such that I will be able to make my input voltage approximately equal Vs, right? We did that. But in this case, I still required current to flow, right? If I have current flowing, that means I have a voltage drop across this resistance, right? It's something I would like to sort of prevent or minimize as much as possible, right? So to minimize it as much as possible, I would like, what did we say here the condition was? V input is equal to Vs times Rp over Rs plus Rp, and we said that we want Rs to be a lot smaller than Rp, right? So this was the condition that we said we want here, right? I would like Rp to be large, or Rs to be very small, but I would still also like to draw a minimal amount of current. I do not want as much, I want to minimize or eliminate this variation as much as possible here. So one way to eliminate, because sometimes I would like this Rp to be high current, right? Sometimes, for example, yesterday we were saying that sometimes I have a sensor and I want maybe as soon as the sensor detects that there is sunlight, I run a motor. For example, for me to run a motor, I need high current. A sensor cannot provide high current. Right? A sensor will not be able to provide high current. It measures the physical phenomena and gives you a signal that is current or voltage. Right? In this case, it's giving me a voltage at the output here that is proportional to this physical phenomena. And it's giving me a small value of current. The small value of current is fine if I don't need a high value of current in here to actuate something. Right? And this is, if I have a need to actuate something, I need a high value of current, what do I do?
Amplifier.
We have yes, we will put a block in here to isolate these two systems from each other. And that's the amplifier block. This amplifier block will sometimes be able to change the magnitude of the voltage, if needed. Or it will only be able to change the magnitude of the current. So in that case, it's called a power amplifier. So we have two kinds of amplifiers we're going to be studying, voltage amplifiers or power amplifiers. Right? And it's the same with the current, the equivalent Norton equivalent circuit approach. We will still need an amplifier in the middle. And these amplifiers will allow us to isolate the two circuits. And because we will power these amplifiers externally using an external power supply, they will draw their power from this external power supply and feed this circuit after that. Right? So we would like to, this amplifier will sort of measure what's coming from my sensor circuit and then process that and feed my output circuit here from an external power supply. But it will feed it with the same signal. So it will take this current, I, for example, or it will measure this voltage here across here and transfer it to the output. Or it will transfer it to the output either with a change in magnitude or a change in power, meaning more current for the same signal, right? So that's what these amplifiers will do. Okay. One thing to note that is the fact that these signals that we will be measuring will have multiple frequency contents. So this is not a sine wave, correct? Since it's not a sine wave, then we know that we can apply Fourier series if this is a periodic signal, or we can apply Fourier transform if it's a non-periodic signal, and we can sort of extract the frequency components.
This will be series and for the concept.
Fourier series, you should have studied that in math. before.
We talked about it, but
Yeah.
we didn't really,
Ah, you did not study Fourier series at all.
no, we talked about it,
No,
but we
we
didn't
Okay.
take it.
Okay. We will again. I will discuss what it does.
Don't
Yeah.
say it like that. I thought you said it.
I thought you knew. But
No.
314, people who took 314 for sure know what Fourier series and Fourier transform are. So, what is 314? What is Fourier series and Fourier transform? Let's say we have this signal here. This signal is not a sine wave, right? So if it's not a sine, if a signal is not a sine wave, I can construct it using a number of sine waves. That's basically what Fourier series and Fourier transform says. Again, we don't need to do the math. And the math related to that is in 314. I'm not interested in the math. I'm interested in the physical phenomena that I'm measuring. Right? So I'm measuring, I would like to measure this signal. This signal is not a sine wave. Since it's not a sine wave, I know that I can decompose it into a set of sine waves. So this signal will have a frequency content at 50 hertz. For example, if this is a periodic signal and this is, the time here is 20 milliseconds, then 1 over 50 hertz is 20 milliseconds. Or 1 over 60 hertz is, 17.6 milliseconds, right? So if this is a periodic signal, I can take Fourier series, apply a tool to it, which is a mathematical tool called Fourier series, and chop it up into components at various frequencies. So I will chop it up into a fundamental component. Sorry, it's not very clear.
X, Y,
I apologize, it's not clear. I'll see if I can get. Dr. Bean only gave me the PDFs. I'll check if I can get the Word document for this. Yeah. But anyway, so I can chop it up into its frequency components. So definitely, if this signal is originally 50 hertz or it's originally 60 hertz, do you expect to see a good amount of 60 hertz component in the system in a signal like this or not? Yes or no? No? Why? I mean, it's if you have a 50 hertz signal, again, a signal basically, or a voltage and a current, they produce power, right? Or why do we have voltage and current? We transmit voltage and current across in a power system to be able to power up our loads, right? So there is power in every signal, right? And this power in every signal is contained at a certain frequency component, right? So I am moving at a certain speed. For example, I'm slow, right? If I'm moving at a certain speed and I'm slow, right, then at another speed, I'm not, and at the speed I'm moving at, I can carry a weight. I can move forward. At another speed, I'm not existing. I do not exist. I cannot able to carry that weight, right? So a signal is very similar, right? If the signal has a 50 hertz component of voltage, and there's a linear circuit that it is connected to, it will produce a 50 hertz component of current, right? That's one of the unique things about sinusoidal signals. Is sinusoidal signals, when applied to a linear circuit, they never change the frequency.
That's why omega, 214 is always the same.
Omega is always the same, right? And your omega t is always the same. So anytime you apply a sinusoidal signal to a linear circuit, no change in frequency will happen, right? So I apply a voltage at 50 hertz, a current at 50 hertz will be produced. This voltage at 50 hertz and current at 50 hertz will produce power. If I have voltage at 50 hertz, let's say, and for simplicity, I will have, let's say I have voltage at 50 hertz. This is 50 hertz. This is V. And let's say I have current at another frequency. Another frequency can be DC, right? So I can have current at DC current, somehow. Okay? This is not a linear circuit now. A linear circuit, we said, I give it 50 hertz voltage, it will respond with 50 hertz current, right? 50 hertz voltage and 50 hertz current. What's power? Power is equal to V times I, right? So if this is my voltage, then, and my current looks exactly the same, I will multiply them by each other. What do I get? 250,000 what? Qatari riyal? Huh? No. What do you mean? No, I'm just multiplying voltage and current. If you multiply these two waveforms, what do you get?
What?
Sure, but what did it look like?
It would look like it's like
No.
It'd just be a higher one.
Yeah, you just multiply the numbers instantaneously. Multiply the numbers.
No.
Right? You will get this. What do I get here for the second half wave?
Lower.
What? No, I don't get
No,
negative.
isn't it positive?
Yeah.
It's
So-
negative.
so-
Yeah, negative times negative is still positive, right?
Oh,
Right? So I get exactly the same. Right? So this is instantaneous power now in this signal. This signal sent, it's a voltage, produced a current because they have a linear circuit, multiply them by each other, this is instantaneous power. This instantaneous power has an average value. And that's what's producing heat in a resistor, for example, or light in a light bulb, right? This signal then has an average value. What is the average value of the signal? Somewhere here, right? What is average value of a signal? Average value of V, or average value of P in this case. Average value of P is equal to what? 1 over the period, T, this is T, right? 1 over the period, integration of the signal over the period, not 0 to infinity, over one period.
Oh, that's the average power.
Yes,
Yeah, yeah.
that's the average value of any signal, right? Average value of any signal is equals 1 over the period, integration of the signal over the period, right? That's the average value of any signal here. So this is average power for a voltage and a current at the same frequency. What if the voltage and current are not at the same frequency? What happens? One case of that is voltage at 50 hertz and current at DC. What is power? What is V times I in this case? What is V times I? This is I. What is V times I?
It's gonna go like this. But then it will have negative.
Exactly. It looks exactly like the voltage waveform, but amplified.
Exactly.
Right? So this is P in this case. What is average value of power in this case? It's equal to 0. Right? So anytime a signal, a voltage waveform and a current waveform are not at the same frequency, they do not produce power. They do not produce power. Right? There's no average power. There will be instantaneous power.
But there won't be average power.
There will not be average power. So it will be useless. So you will not have torque on a motor, for example. You will not have light on a light bulb. I mean, it's right. There is no average power produced. There will be voltage and current produced, but the average value will be 0. So you will have a motor doing like this, for example. Torque, the motor shaft will be going back and forth, doing nothing. Right? There's no average ability to produce average torque because there's no average power in this case. Right? So signals will have power at their frequency, at the frequency that they exist at. Right?
Yeah.
So that's where we use Fourier series to analyze signals that are non-sinusoidal. This is easy because it's nice and sinusoidal. If it's non-sinusoidal, a signal will still have power, right? And it will have power components, not a single value. It will have power components. So a signal can have. So I have a fundamental. This is 50 hertz, and I can have a third harmonic. Third harmonic. How do I draw a third harmonic? It will have in the same half wave. It will exist 3 times.
Yeah.
Right. If this is 50 hertz, for example, this will be 150 hertz. Right. Right. This is 150 hertz in this case. If I add them together, I will get what? What do I get? I get, okay, here at the beginning, they both added up, so maybe I get something that looks, it will rise faster than both of them because I'm adding 2 numbers here. And then, let me put the original 50 hertz here just to help me draw. Right? And then what's happening? Then this blue is slowing down a little bit, and this green is there. So I'm adding these 2. So I'm gonna be greater than this red one.
But then it's gonna drop.
Exactly. I will then start dropping here. Right? So I will look something like.
I think not like that. Because isn't that one of them is positive and one of them is negative?
What do you mean? I'm adding. Remember, I'm not multiplying.
Oh, you're adding.
I'm adding. I'm creating a signal with multiple harmonic content. That's what I'm doing here, right? So if I'm creating a signal with multiple harmonic content, this is an example of a signal with multiple harmonic content. This is not a sine wave, right? So my original question to you was, okay, now this is at 50 hertz, this is at 150 hertz. I added them up and they created a signal that looks funky, right? That does not look like a sine wave. If I want to use Fourier series or Fourier transform and I apply it to this waveform, what do I expect to see? I expect to see what?
Sinusoidal.
Hmm?
Sinusoidal way.
Remember, I said that Fourier series or Fourier transform takes my waveform, which is non-sinusoidal, chops it up into the component sine waves. Component sine waves. No, it's not the discrete. We'll talk about the discrete. Sure, it will be the discrete, sure. But it will take this and chop it up into the component sine waves. These component sine waves will exist at what frequencies? In this case, it will exist at omega naught, which is 50 hertz, and 3 omega naught, which is 150 hertz. So if I plot the power spectral density, or if you've taken 314, you will know what power spectral density means. It's the power of that signal at that specific frequency. How is power measured? Remember, average value of power. What is average value of power? Is 1 over the period integration of the waveform over the period, right? Right? So what is this integration? Integration is what? Integration is, graphically, it's the area under the curve. Right? So the larger the area under the curve that I have, the more power. So if I consider this voltage waveform, the 50 hertz waveform, versus this blue waveform, which has larger area under the curve, assuming they're both positive, okay? Because the 50 hertz, right? So Fourier series will do the same thing. It will show that at 50 hertz, this will have a larger power spectral density. The power at that spectral density, at that spectrum, at 50 hertz, will be higher because this waveform originally had a larger area under the curve in the time domain. Okay? So that's 314. I don't want to talk about 314. But the reason we talked about this is because now we have a signal that looks like this. This signal, I would like to send it through my amplifier. Right? I will design, when I design my amplifier, I have to make sure that I'm going to consider signals that are non-sinusoidal. What is this amplifier going to do with these non-sinusoidal signals? So that's the reason we discussed this, actually. So I would like to make sure that I transfer this signal that is non-sinusoidal through to my signal, because I want to transfer it to the signal conditioning system. I want to process it later, add things, multiply things. I want to bring it into my computer, right? So for me to bring it into my computer, I have to make sure I can process it. For me to process it, I have to measure it. I have to measure it, and then sometimes I have to amplify it, because my computer accepts analog signals between 0 and 3 volts, for example. And the sensor is giving me a 0 to 10 microvolts. I need to take that 0 to 10 microvolts, amplify it using my amplifier. So the amplifier will have to process the signal that is non-sinusoidal in this case. So you have to characterize the amplifier to make sure you understand how it's going to operate for a non-sinusoidal signal, right? That's the objective of what we want to do. And this non-sinusoidal signal can sometimes be pure AC, or it can have a DC component as well. We talked about this last time. If it has a DC component as well, sometimes you will have to maybe remove that DC component originally before amplifying it. And then if you want to add a DC component later because your signal conditioning system requires that, you may have to do that again. Right, so this is back to the op-amp circuits. So this is the relationship between op-amp circuits and the amplifier circuits, right? So op-amp circuits can sometimes be used to add and subtract DC levels, for example. So I have a signal here that has a component that is AC and DC, right? This is if it's not sinusoidal or if it's not pure DC, then it has some AC component, right? That's signals can either be AC or DC. This wiggly signal here has an average value, which means it has a DC component. And it's not a flat signal. That means it also has an AC component. So if I take this and chop it up using Fourier series or Fourier transform, I will find components at many different frequencies. right? So I need to make sure that I'm able to process something like this. So I have to characterize my amplifier for various frequencies, right? And that's going to lead us to the frequency response stuff that is similar to 314. And we do this in the frequency domain. Remember, I just drew the curve, this curve that I drew, or this plot that I plotted here, had an axis of frequency. I said that it has the signal will have a component at 50 hertz. For example, it will have some magnitude at 50 hertz, x, and it will have another magnitude at 150 hertz. That's the signal that we had. This is a representation of what? Is a representation of this signal. Correct? Which is also can be represented as two time domain signals, the 50 hertz and the 150 hertz signal that, so I can chop this up into these two, right? So this is what Fourier series does to me, right? It gives me the sinusoidal components that make up a non-sinusoidal signal. And then both of these, yes ma'am.
When you say make up, it means add up?
Yeah, add up, yeah, compose. Yeah, addition, yeah, addition. I'll show you an addition of, square wave and how sinusoids are added up or to create a square wave. I will show you that right now. Right? But yes, added up simply, like we just did. You add up these two and they will equal this. This, for you to go from here to here, it's Fourier series or Fourier transform if it's not periodic. That's the difference between them is for 314, not for us here. For us here, we just need to understand that it has multiple frequency components. And these two waveforms are in time domain. Right? I'm plotting or analyzing the signal here in the time domain. How about this? What is this called? This is frequency domain, exactly. Since this is the axis here is frequency. So signals can be represented both in time domain and frequency domain. Okay? So amplifiers, the amplifiers that we have to design, we will design in both time domain and frequency domain, because we have to design them in frequency domain because it's easier to design them in frequency domain, right? And then you can look at their time domain response, and we will have an example here that does both. So it gives you analyze the signal and you analyze the system in frequency domain, and then look at what happens to a signal in the time domain, right? So this is the differentiation between the two systems. So frequency domain, time domain, that's what we talked about. Again, these signals, any sinusoidal signal can be represented, using its peak value and frequency, right? So this is a sine wave. We can define this sine wave as an equation using its peak value, VA in this case, and omega, which is its frequency in radian per second. Yeah.
What is sine?
No,
You usually build with cosine.
doesn't matter. I'm just saying here. I have a sine wave signal. You can, in Fourier series, there's a process to create a sum of sines to represent a signal, and then there's another format for Fourier series to create a sum of cosines to present a signal. So you can do both ways, and I'm sure in 314 you will cover that. But you can do sine or cosine. But a sine or a cosine, both of them can be represented as, you can define the signal using its peak magnitude and its frequency. That's really the way you can represent a signal. Yeah. So here's an example of a waveform, a square wave, for example, and this is its Fourier series representation. So note here that it's dot dot dot. This dot 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 means actually goes to infinity. So a square wave. Remember these square waves have these high transitions, like the impulse function. Remember the impulse function? Impulse function has what frequency content? All the frequency content, right? What you studied the impulse function, right?
We talked about.
You talked about the impulse function.
Yeah.
Okay. How do I approximate that? If I'm driving the car at a certain speed, you know that I'm driving at a specific speed. But if I'm ramping up, right? If I'm accelerating my car, the car has a component at low speed. The car has a component at a little higher speed, a little higher speed, a little higher speed, a little higher speed. When you add them up, you can reconstruct what the car is doing. It's like this Fourier series, right? So I have a wiggly waveform. This wiggly waveform, I chop it up into sine waves. these sine waves, if I add them up, they will tell me what my signal was. Right? So just here in a case where I have very high transitions, if this is a slow transitioning waveform, it will be much closer to a sine wave. Right? To a single, like the waveform that I drew, this waveform that we drew here, this waveform had only two components. This, if you analyze it using Fourier series, only have two components. The 50 hertz and the 150 hertz, right? But if I have a square wave, no, a lot more. This transition here can be represented using an infinite series of sine waves. It's just, it will contain, okay, this square wave here, let's say is at 50 hertz. So you will find that you can, one component of this waveform will be at the same frequency, right? And then, okay, look at the difference between, here, let's redraw it here. It's my square wave. So one component will definitely be at the same frequency, for sure, right? Because we said we were going to add these up to create this one. So how do I add more to create this? I add something at, so this is at, let's say, 50 hertz, fundamental frequency, omega naught, right? And this let's say I'll add a third harmonic, 3 omega naught. Right? Add these two together, fine. I will get something that is a little bit higher, rising than both of them, but still not as sharp as the square wave rise. Right? So, okay, maybe I need to add a 5 omega naught. I'm not going to draw. I'm not an artist, so blah, blah, blah. Right? So the idea is, okay, what's happening here? You add more harmonics. This will rise faster, rise faster, rise faster, until you create something that rises as fast as your square wave. Right? So your square wave will contain so many harmonic components, right? But at some point you have to stop, right? At some point, okay, I mean, if it's rising, from zero, if it's rising from zero to voltage level V in no time, then it's impossible to reconstruct it.
Is it like Taylor series when approximating the graph? You just keep going.
Fourier series is Taylor series expands again a waveform, a function of x, y equals f of x. Taylor series expands y equals f of x. A Fourier series expands y equals, some funky function that is periodic, right? So it's similar sort of understanding. But think of it. Think of this addition business, right? Let's see what's happening here. What's happening here is I want all of these waveforms, because again, any waveform I said can be reconstructed using sines. So I want these waveforms to all rise as fast as a square wave. So I keep adding more. I keep adding more of them. So I keep adding more of them until I'm able to match this square wave, right? So at some point I will be close enough. I will never be able to match it. Never be able to match it. Because these square waves have an infinite amount of ideal square wave that rises in zero time, like an impulse function, you can never match. But if it has a certain slope, you'll be able to match it with a certain limited number of sines. If it's an ideal waveform, ideal impulse like rise, and it's impossible to match it. But at some point you have to stop, right? You're close enough, right? So I need to be able to now do what? If my signal, my sensor is producing something like this, and I want to send this to my signal conditioning system, my processor. How do I do this? I have to pass this to the amplifier. The amplifier now needs to deal with frequency content in all this bandwidth, right? So let's say I have to filter, I have to amplify. Can I filter content that is useful? I cannot filter content that is useful. If I want to pass this signal to my signal processing system to do some calculations, I have to make sure that I am passing the right signal through. So my amplifier has to deal with the signal without distorting it, without changing its shape, without eliminating useful frequency components, right? That's where we will have to design your amplifiers in the frequency domain and see what the effect of your amplifier is on the signal's frequency components in the frequency domain. So again, we don't need to understand Fourier series besides the fact that it's a chopping up of any non-sinusoidal signal to a sum of sines or a sum of cosines that is actually infinite in nature, But at some point you are able to match the signal that you want close enough. That means if I want to pass this signal through my amplifier, and I'm stopping at the fifth harmonic, that means my amplifier should deal with everything up to, let's say, 50 hertz times 5. Right? So up to 250 hertz, the response of my amplifier should be flat. It should be something that will not affect or distort your signal up to 250 hertz. Right? We talked about this. So again, the difference between the output of Fourier series and the output of Fourier transform is the fact that Fourier series is applied to periodic signals. So something that keeps repeating. Right? It's non-sinusoidal, but keeps repeating. If you have a waveform that is just wiggly waveform, that is, so it's non-sinusoidal, but it's non-periodic, then you have to apply Fourier transform. With Fourier transform, you don't get discrete frequency components like we got for Fourier series. Right? That's the difference between Fourier series and Fourier transform. Fourier transform gives you a waveform of frequencies. So you can, at any point in time here, you have a frequency component. I mean, here it's Fourier series discrete. I have at omega naught, 3 omega naught, 5 omega naught, 7 omega naught. I have nothing at 1.5 or at 2.5, right? Because the signal was periodic. If the signal is non-periodic, you analyze it using Fourier transform, and the Fourier transform output is a continuous set of frequency components. So at omega naught times 1.1 times 1.2 times 1, you will have a continuous waveform of frequencies. Right, so I mean, just a subtle difference between them. Yeah. Okay, now I need to take this signal now. Again, I have to eventually processes it as well. So it was analog, right? This signal was analog, and my amplifier will then amplify its voltage, magnitude, for example, and maybe the current as well, right? After that, I have to send it to a processor, right? This processor is a digital system. This digital system will have to deal with digital signals. So I have to take this signal that I have, and that's not the core of the course. The core of the course is the analog signal processing. But there's a section we need to talk about here. So I will have my input signal like this. I need to feed it. I've amplified it and done whatever I need to do with my amplifier stage. For the computer to start processing it, the computer deals with what? Digital signals. Right? Digital signals, you've talked about in 214, you know what a binary signal is, right? If I have a binary 3-bit binary, I'm storing my information in 3 bits, right? I can do what? How many levels or how many words can I write, or variations of 3 bits can I have in a digital form? 2 to the third, exactly. So 2 to the third is 8. Right, so I can start with 0, 0, 0, and then I end up with 1, 1, 1. You didn't take in 214?
248.
Or 248? Because I teach 215 last semester, and I thought it's very similar. Yeah. So anyway, in 248, you took this. You did not take 248? Okay. It's fine. So let's see. Most of the class didn't take 248?
I took it.
Okay. So in digital systems, right? In a digital system, computers do not understand. So, but to know gates, you do not study gates at all. In 214, you don't study gates at all.
No,
Logic gates.
that's 248 entirely.
Ah, okay. I didn't know that. It's okay. It's not a big deal. And we'll go through something. So you'll learn something interesting. So anyway, so computers only understand inside the computer. Okay. So first I have my sensor. This sensor, I have to do some amplification stage, which is the core of our course. And then there's this computer here that only understands ones and zeros. Computers do not understand analog signals. They do not like to deal with analog signals. They like ones and zeros. So to move from this amplified conditioned signal to ones and zeros, you have to sort of quantize your signal. It's called quantization of the signal. For me to quantize the signal, I have to know how am I going to deal with it inside my computer. So let's say I have a computer, when you go buy a computer today or when you install Windows, I tell you it's 64-bit Windows, right? Or 32-bit Windows. What does this mean? The architecture. So architecture refers to how data is stored and processed inside the computer. So let's say we have a rudimentary, very basic computer that is 3-bit computer. Windows, my age Windows. We had DOS at my, when I started playing with the computer, we had DOS. I don't think any of you played with DOS. You played with DOS? Come on. So and we had dial-up internet, and we didn't, no images. You have to download everything, and then you have to.
It takes a long time.
Sure, I'm not that old, but it's fine. Okay, so let's say we have a 3-bit computer, right? This 3-bit computer means 3 bits means it can store data in 3 bits only. That's the only thing. I mean, again, it's a simplified. You cannot put anything larger than 3 bits. It will truncate. It's 248. Let's not get too much into that. Okay. So, but basically, let's say you have 3 boxes. Let's say you have it's raining, and it's windy, and it's sunny. Raining can be 1 or 0. Windy 1 or 0. Sunny 1 or 0. Right. So then, if the word inside here is 1, 0, 1, then it's rainy, windy, and rainy, not windy, and sunny, right? So then it pops up on the screen, and Abdulaziz is happy. Yesterday I can go fishing, right? So this is how the data was represented. But how many variations can I represent in 3 bits? 8. I can only put 8. I can start with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1,
0. 1, 1, 0.
1, 1, 0?
Yeah, 1, 1,
1,
0.
2, 3, 4, 5, 6 is what? 1, 0, right?
And then 1, 1,
7 is this, exactly.
1.
So I can 0, 1, 2, 3, 4, 5, 6,
Missing 1.
7. Why? No, it's 0 to 7. 0 to 7 is 8. 0 to 7 is 8 variations, right? So 0 to 7 is 8 variations. So I can store only 8 types of information or 8 information points in 3 bits, right? So my signal that's analog, in the analog domain now, I have to bring it into this digital domain. So I have a signal that's the sine wave. For example, I'm only allowed to deal with 8 different pieces of information. I can only deliver 8 pieces of information. So how is the computer going to deal with this? The computer will deal with this as if let's say I chop this up into 8. I don't know if I'm going to draw 1, 2, 3, 4, 1, 2, 3, 4. And you get the picture, right? So 4 on top and 4 on the bottom, right? So the computer also, so this is sort of 8 levels that I have to only deal with 8 values of the signal. Do we agree that I can only deal with 8 values of the signal if I'm going to use a 3-bit computer? Okay. And if I'm going to deal with these 8 values, computers also are not continuous time. A computer you buy a computer now, 2 gigahertz, right? Or 2.7 gigahertz with overthreading, blah, 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 gets to 3, right? Something like that, right? What is that? That is the frequency of the clock that is running the computer. And each operation in the computer is done at that speed. So each operation in the PC or in a digital system is operated based on the clock frequency. So the system, the computer is not an analog. It cannot see a continuous time domain signal. So what do I have to do? I have to take my time domain signal and then chop it up in 2 ways. One way, sideways, which will sort of limit the number of values that I have in my signal, that the computer can process in my signal. The other way is how fast I can process this, how fast the computer operates. The computer operates, let's say this is 20 milliseconds, for example. Let's say my computer is, I don't know, it's the clock frequency, the period of the clock is 5 milliseconds. So I have every 5 milliseconds I will do a calculation, or I will do a measurement, or I will do something every 5 milliseconds only. Exactly. So I have to now. The computer is not going to see my complete signal all the time, right? The computer will see the signal at discrete values. because of its clock frequency, right? What else? It will also see the signal quantized at discrete levels, limited by the number of bits the computer is able to process. So, and between these two levels, between this time t1 and time t2, the computer cannot see, right? It will only see the last values measured. So it saw this value here, and it saw this value here. So it will preserve the value here, store it in this, take this value here, store it in another variation, right? So let's say this the lowest point here represents 0, and this highest point here will represent 7. So the computer can see 0, 1, 2, 3, 4, 5, 6, 7. Yeah, I can see these 7 levels of 7 values of the signal magnitude, and it can see these 7 values of signal magnitude only at discrete periods of time, right? So this idea of sampling the signal and then maintaining its value until the next period of sampling is called quantization, right? So I converted my signal, I sampled here, this is the signal for this duration. Sampled here, this is the signal at this duration. Sampled here, this is the signal at this duration. Sampled here, this is the signal at this duration. Sampled here, this is the signal at this duration. Sampled here, this is the signal at this duration. So I converted this sine wave into something that looks, something that looks like a sine wave, right? If I increase these numbers of bits, what's going to happen to my sine wave?
It's gonna look more like
It will look more like a sine wave. So the higher the number of bits, the less information you lose, right? And the higher the frequency of sampling, the less information you lose. Because remember, every time you sample, you will quantize the signal, meaning between one sample and the next, the signal will be the same value, right? So you still lose some information. Even if you have a lot of bits, you still lose some information, right? So that's why you want clock speeds that are super high. And you want number of bits that are very large, because you want your information not to be lost. You want to be able to look at the screen, because again, your screen output is an analog. At the end of the day, this transducer, this screen that you're looking at is analog. This is the interface between you and the computer. You're seeing this analog signal. It's not the digital signal that's happening, right? So you want to see a nice signal. You want to hear a nice audio, right? So this is going to be dependent on the sampling frequency and the number of bits of the computer system. Yeah. Okay. What about noise? Noise is part of what? If it's noise, that's going to be part of the measurement noise. So you're saying, for example, I'm measuring current, or I'm measuring light intensity, but Abdulaziz has a laser pointer, and he's playing with it. He's adding noise to the. I'm sorry to pick on you, but yeah. But so there's this laser pointer. This laser pointer is going to be doing what? Modifying the light intensity. But this laser pointer, laser light is at a very different frequency than ambient light. Or if you're measuring ambient light, these two are at different frequencies, right? So they will be at different frequencies. So the sensor will produce a signal that is, in this case, not sinusoidal. It will be sinusoidal at, to have a component at the frequency of the visible light, and the component at the frequency of laser light, for example, right? So then these two components, you're going to be passing them through. You're going to be passing them through a process, to an amplifier. This amplifier circuit, we are going to design it in the frequency domain. So we will kill any signal that we do not want to see by designing it properly in the frequency domain. Okay? So we will have to deal with that in the analog domain. Yeah. But you could also, additionally, if you know that this is existing after you've sent this into the system, you can also deal with that with digital filtering. That's what we study in 444 and 448. Nobody took 444, right? 444? Yes, sir.
For the noise, you're sending amplifiers, right?
Yes.
So wouldn't noise be amplified?
No.
If it's in the pass band of the amplifier. But we will attenuate it.
Okay.
So we will design the amplifier such that we look at the frequency domain. Okay, any signal that is beyond 100 hertz, we will attenuate it. Any signal that is less than 100 hertz, we will make it pass. We can amplify it. We can do whatever we want. Okay, so this is, again, this is my original analog signal. And then this is these are the time steps at which my computer operates, my digital signal operates, right? At every time step, I'm gonna sample the signal using what is called an analog to digital converter. This analog to digital converter will quantize my signal. So between this point and this point, I'm preserving I only have in memory this last point, this last value that I have here, right? And can this value be anything? No. The value here is going to be limited by the number of bits that I have, right? Remember the horizontal lines? So this sine wave, I can only chop it up into 8 different values. So 8 different values at various points in time, depending on the frequency of the processor, right? So that's what this is talking about here. We just introduced idea of, this is, the idea of sampling, and this is called now a discrete time signal, and that has been quantized or discretized using, and it will depend on the number of bits. Again, bits are ones and zeros, right? Bits are ones and zeros. So if you look at this, what we consider 3 bits that we had, right? Our 3 bits. We said 0, 0, 0. That's 0, 0, 0, 1, 0, 1, 0. Why did I? The way we construct, for example, a number.
4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones.
Sure. So we call this a 3-bit memory location, for example, and we call this the least significant bit, and we call this the most significant bit. And the way we go from the sine wave, value that we measured here. Let's say I measured here something that's equal to, remember we said we're only limited to 0, 1, 2, 3, 4, 5, 6, 7. So let's say I measured 2, right? What will this 2 correspond to in this digital storage bin that I have? 2. I measured 2. Yeah, it will correspond to 0, 1, 0. So this is 0, this is 1, and this is 2. So how did we come up with that? The way we come up with that is, the way we look at this digital train or digital stream of bytes, of bits. So this is bits. These are bits. These bits compose, if you have 8 bits, it's called a byte, right? So we don't have a byte here. We're even less. We're just 3 bits here. So this stream of bits is called, is something that you can actually measure. So what will this look like? 0, then 1, then 0. This is what you would measure if, for example, you're sending those in a series, right? The way we construct numbers, or we move from these decimal numbers to, we call these binary numbers, is by adding weights to each of these places. So this is sort of the zeros place. So this is 2 to the 0. Numbers here would be weighted 2 to the 1. Numbers here would be weighted 2 to the 2. And how would you construct? You go from this value of 2 to this representation. You would do this. You would have in the 2 is what? 2 to the 0 is
0.
no, 2 to the 0 is 1, and 2 to the 1 is 2 to the 1 is 2, right? So I would like to do what? I would like to, let's look at it start from this weighted from this right to the left side. So I want to construct 2 decimal, convert it to a binary. How would I do that? I would like to add something multiplied by 2 to the 0 plus something multiplied by 2 to the 1 plus something multiplied by 2 squared, right? Something multiplied by 2 squared, and make that equal to 2. So exactly, so that's 0, 1, 0. And that's why, so you take the 0, 1, 0, this is 0, this is 1, this is 0, you construct it 2. You can construct 3, 4, 5. Again, you're not going to be tested on this decimal to binary conversion, but the idea is, we're just talking about converting from an analog signal to a digital signal. So these digital signals will be limited by the number of bits, right? And this is what we were just talking about here. So bit 0 will be, in our case, 0, 1, 0, right? That's what we constructed, and this is the least significant, the most significant bit. Still have 2-3 minutes. Again, so now I converted this to digital. How is this physically done in a modern electronic world? This is done using an A to D converter. So after my amplifier, this is going to go into an A to D converter. This A to D converter will quantize the signal, and then take the quantized signal, which is 2 or 3 or 4 or 5 or 6 or 7, and convert that to binary. That's the job of the A to D converter. And then it will spit out, or I don't know, spit is a bad word, but it will produce a binary stream of bits that will represent your analog signal. And then there's a reverse of that, of course. There's a digital to analog converter. This digital to analog converter is, let's say you're creating music on the computer. You want to listen to that. That's an analog signal. So a digital to analog converter will then take your digital stream that you're programming or doing whatever you want to do with, and then convert it to an analog signal. This analog signal needs to go to a speaker, sorry. This speaker requires power to drive it. So you will take your digital signal, convert it to analog, amplify it. This is again where we come in with this course, right? We amplify it, and then we convert it we amplify it, and then apply it to the speaker. Yes?
So an example for an A to D signal is you move the mouse and it moves in front of you. So you're giving an analog command that turns into a digital, and the opposite is the sound coming off the computer, which is deep.
With today's mouse, I mean, again, the ball-based mouse, the ball-based mouse that we have, they used to have balls before,
Yeah.
right? What is this doing? The ball is changing a roller. This roller is probably connected to, is going to be connected to something that says, okay, I've moved 1 centimeter in the X position, I've moved 1 centimeter in the Y position, I moved X and Y, right? So I've moved 1 centimeter here, 1 centimeter here. So it will take, so maybe there's a position sensor. Again, I don't know how the mouse is constructed, but there's probably something that is measuring the number of rotations in the X direction, measuring number of rotations in the Y direction. This can be analog or can be digital. So I don't know, I'm not sure. So it can be digital because there are sensors that are called Hall effect sensors. Hall effect sensors produce a pulse, for example, every rotation. So it can be a pulse every rotation. So I can be counting these pulses. So maybe it's not analog, I don't know. I can merely be counting these pulses and producing, okay, in X I move this number of pulses, and Y I move this number of pulses. So we need to look at the design. That's a good design project if you want to do that for course projects instead of the boring simple amplifier that we are proposing. I'm happy to do that. No, I'm serious. If you're interested in, okay. So then you want to do a boring, but I'm happy again, guys. I'm happy if you want to, because the class project is on the website. But if you want to do something more interesting than building something which is something similar to what you're going to be doing in the labs, I'm happy to entertain that. So if you want to look at a circuit that is interesting, and come on and build a project based on that instead of, and you don't have to build it in that case. Maybe do some simulations and show me draw a small circuit to represent that and explain how it works. I'm happy to entertain that. You don't have to do something standard and boring. So I'm okay. You want to do something standard? You're okay with what? With the standard interesting stuff. Okay, that's fine. Okay, so we'll stop here. Tomorrow's class will continue. I promise. Tomorrow's class we'll start having some equations. Today recitation. Tomorrow, yeah, because tomorrow we'll start having some. Yeah, because exams next week. Yes.
So
Don't remind me.
So there's one recitation for